In this problem, we're going to consider another homogeneous system. We're going to know the eigenvalues and eigenvectors. Those are pre-calculated for us. And now we're going to phrase the question a bit differently. What we'd like to do is find initial conditions for which the solution is going to tend towards the 0, 0, or the origin, as time gets larger or heads to infinity. Here's the chain of logic we can use for that. The solution that comes out of this first eigenvalue-eigenvector pair is e to the 3t 1, 2. That's x1 of t. The second solution is e to the negative 2t, that eigenvalue, times the eigenvector that goes with that, 1, 4. If we look at those two solutions, this is the one that heads towards 0, 0 as t goes to infinity. So if we want to know initial values that will converge towards 0, 0, what we learned in the earlier work is that we need to pick initial values that are multiples of the eigenvector 1, 4. If we do that, our general solution would have none of this solution and all of this, some multiple of this solution. And so we could pick, say, 1, 4 is a perfectly good initial value. Or we could also pick, sorry, these should have vectors. Or we could pick, say, x naught is equal to -3 and -12. That would be just as good. Any multiple at all of that 1, 4 vector will converge towards 0, 0 in the long run because of that negative exponential multiplier. Now, there's the flip side of that question. What if we wanted a solution that moved away from 0, 0? Now, one temptation, which is totally reasonable, is to think of this second solution, and we could use a multiple of 1, 2. Because this part here, this exponential here, heads towards infinity as t increases. And that would be totally fine, it's true. However, it's worth noting that it's not necessarily required. There are many other choices because the general solution looks like x is c1 e to the 3t times 1, 2 plus c2 e to the negative 2t, using these values here, 1, 4. Looking at this, if we pick any initial condition that is not a multiple of the one that does go to 0, of 1, 4, then what happens there? We will have c1 be non-zero, and as soon as c1 is non-zero, the c1 e to the 3t 1, 2 part of the solution is going to grow or move away from the origin from 0, 0. So in this case, it's actually more broad. Any value that's not just this exponential, that includes even a little bit of this one, is going to head towards infinity or head away from the origin as time increases. This is one of those special cases of, if you want something to shrink, it's got to be this vector. If there's any of this vector, it's going to grow forever. It doesn't matter what this vector does, because it's going to become less and less important because of this diminishing negative exponential. Let's see that graphically. Again, we have two eigenvectors. One of them is 1, 2, and that defines a line like so. And this is associated with the e to the 3t, or exponential growth. And we also have the other vector, which is the 1, 4 vector. So here, there we go. That's the 1, 4 vector associated with e to the negative 2t, or exponential decay. So what we know from that is, if we started on this line and only on this line, the solutions are going to head towards the origin. That's what we said for our first answer. If we start on this other line, we'll have a straight line path away from the origin, absolutely. But any other point that we pick, let's say this one in the middle here, there's going to be a decay towards this direction, but an expansion out in this direction. And what we typically get is loops coming out like this. Or if you picked a point here, again, it's a mix of some red and some green components, a little less visible or easy to see with these almost parallel vectors. But the directionality is going to be swooping in towards the origin, but then going out along the green line, because that line corresponds to an exponential increase times that vector. So a larger and larger multiple of that vector in the long run. And likewise, if we picked a point here, it might do something like this. And so this point, if we started there, would end up pushing us away from the origin in the long run.